the Lagrange method with multi-constraint. In a lot of cases, in real life, you not only have one constraint, you have a lot of constraints. For example, I want to achieve as much as I can, but I constrained by the limited time, the limited money, the limited opportunity. So all limited, we call it a constraint. You most probably have multi-constraints. So to make it simple, again, I have an objective function f, have 3 variables, and give you 2 constraints, g and h. Then the same principle. The Lagrange method tells you this gradient of f must be coplanar. In geometry, this is a coplanar of the gradient of g and the gradient of h. And then you write as a linear combination of lambda times the gradient of g, mu times gradient of h. Do you remember? If I give you a vector A here, another vector B here, the whole, any vector C here on the plane is going to be C1A plus C2B. And that's exactly, you can put this as lambda, this as mu, that's what it says. That means, similar idea, the gradient is going to be parallel to both A and B. See it? Because it's under the component, it's parallel to the plane made by gradient G and H. Let's look at an application. In this application, I got 4 variables, x1, y1, x2, y2. I got 2 constraints. The x1, y1 stay in the same circle, x2, y2 stay on the same circle. So basically, I have 2 circles, x1, y1, x2, y2. And this x, y, the 4 variable, you choose from the 2 circles, but I want to maximize this. x1 times xy1 and x2 times y2. Well, I write it down, these 2 constraints into this equation. I write this objective function like this. And then, how many equations I have? How many variables I have? Well, I write it down the gradient. Let me get a little more page. Okay. So take the gradient of f. 4 variables, right? Keep that in mind. The gradient of f, take to x1 is y1, take to x2 is to y first. And then take it to the y1 is going to be x1, take it to x2 is y2, take x2, that's x2. That's the gradient. The gradient of g is going to be 2x1, 2y1, 0, 0. The gradient of h is 0, 0, 2x2, 2y2. So you got the 4 equations here. And also, you got another 2 equations. Got 6 equations. Wow. 6 equations, 6 variables. Because x1, x2, y1, y2. 4. Add the lambda, add the mu, sounds terrible. But quickly you're going to observe the symmetry and the very easy exercise you're going to find. x1, x2, and the y1, y2, they all equal square root of 2 over 2. Basically, all you need, as I pointed out the last time, is right here, 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 and here, here. That's how you get the maximum minimum. Depends on negative or positive. So you can get the critical points, and then you're going to get the maximum. I would think very easy to see the maximum is going to be 1. The minimum is going to be negative 1. That's it. Well, the last example I'm going to show you is not perfect. In what sense? In a sense, you cannot run out all constraints with the equation. Let me show you why. I try to build a rectangular box like this, box. That's a rectangular box. But I have the surface area. Maybe you build by plywood, totaler. This is surface area, 1,500 square feet. And you might build this by the 2 times 4, the pillars of those logs. And the total length is 200 centimeters. And what you need is to find the maximum and the minimum volume. Well, minimum is easy, get a 0, flat, common sense. But how to find the maximum when you only have this much material to make it the edge, make it the board, the surface? So we get 2 constraints, the constraint of the surface, constraint of length. We want to maximize the volume. Looks simple. And the surface constraint is this equation, equal 1,500. The sides, you have 12 sides, must be equal to 100. And the volume is x, y, z. So you get 3 plus 2 multiply 5 variables and the 5 equations. So what is the gradient of the volume? The gradient for volume is yz, xz, xy. That's the gradient. The gradient of the h is this. Take a derivative to x, that's 2y. Take a derivative to x, that's 2z. And take a derivative to y, that's 2x. Take a derivative to, that's 2z. And that's the gradient of the s. That's the gradient of f. And if you take a derivative to the sides, you'll get 4, 4, 4. That's the gradient of the dimensional, the d. So the Lagrange method give you 3 equations here, 3, 4, 5. And you have the first 2 equations, 1 and 2. Well, of course, you can solve it. But they say, oh, how can I solve that? It's too complicated. No. If you subtract, you quickly find, doesn't matter how do you do it, the x always equal y equal z. You look at this equation or that equation, they're all equal. Because the symmetry, obvious symmetry. If they're all equal, so what? You just try to get the maximum, and what you do, you're going to let x equal y equal z plug into the total length, which is 200. So you get this x equal y equal z equals 1/3 of 50. But does this solve the problem? Well, you plug into the surface area. Does not work out, because if we multiply this solution, you find this bigger than the constraint, which is 1,500. That does not work. Well, if you plug in the x, y, z to the second, the surface constraint, Then you're going to find your x, y, z equal this number, 5 square root of 10. And then you double check if it is under the constraint of your total side lengths. When you add together, it approximates to 190, a little less than 200. You are good, but there's only one problem. That does not all fit. It's not equal to 200. It's really less than 200. That's really a common sense solution. In reality, you may not run out all constrained materials, something left over. In this case, we left over a little bit of the side lengths, like those. That's fine. That's now optimized solution. The total volume is 3953, round up. But to give you a little food of thought, and this problem is not quite set it right. It's not set it right. If I needed to change this a little bit, what I'm going to change is instead of equal, nobody said you have to equal. You have to be less. You cannot make what you don't have. That will be our next topic. We call it simplex method. And we still use Lagrange method, but it's a little more complicated, but more realistic, more useful. And this example just showed you the traditional method in your calculus will not work for such an example. So why I said that does not work? Because this really does not equal. In the end, it's not equal. What you get? It's 189. It's not 200. So it's better to remodel the problem into less instead of equal. That's a more common constraint. Thank you for today. Next time we're going to see more realistic problem and the simplex method to solve the maximum and minimum problem. See you next time.